Alright, so just want to make a little video to try to catch up. As you know, we missed a day from snow, and so just to pick up the pieces here, look at Chapter 2, hopefully tell you what we haven't covered yet in here. So in particular, the very start of the chapter, I actually give one possible way of constructing matrices. So that's kind of something that I was blathering on about in class, like how would you do it? Well, here's how, it's right there. But that gives a foundation on which we could assume that two matrices would only be equal if they're equal if every component matches, right? We talked about this notation, rows, columns. All right, move along here. Oh, one comment. This is I think no longer a. I should make a correction. I have 5 children now. I can no longer use this matrix. Oops, don't tell my little one. There's our definition. 2 matrices are equal if and only if they have matching components. All right. We talked about transpose, right? One of the things I have said, but here it is nicely written. The jth row of the transpose of A is the jth column of A transposed. That's kind of useful to us at times. And likewise, the ith column of A transpose is the ith row of A transposed. So those are kind of neat. I hope you've picked up on the fact that this notation means that. All right. First day, I defined matrix addition and scalar multiplication. You may recall these were the definitions, right? These are the properties that we have. Matrix addition is associative, commutative. Scalar multiplication distributes across matrix addition like that. Scalar addition distributes across scalar addition distributes across scalar multiplication on a matrix like so. We can either multiply the numbers first, then multiply the matrix, or we can multiply the matrix by the first number and then multiply by the second number. And of course, 1 times a matrix is a matrix again. All of these things we could prove with little index calculations like this, all right, or that. I've talked a lot about that in class. I'll let you read the other ones. Here's the 0 matrix we mentioned. Another thing I have not said in class, but it's probably worth mentioning, is that if we take 0, the number 0, and we multiply by a matrix, scalar multiply a matrix by that 0, what do we get? Well, we get the 0 matrix. No surprises there. All right. Here's the proof. 0 times any matrix, the ijth component of that, is by definition 0 times the ijth component of the matrix, but 0 times anything is 0. So we've shown that the ijth component of 0 times a is 0 for all ij. Therefore, it follows that 0 times a is 0, right? And here's the proof that the matrix with all zeros actually behaves as advertised here in part 2. We've talked about the Kronecker delta sum in class already, so I won't belabor that. We've talked about the standard basis, right, that you can, depending on context, E1 is either just 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, etc., etc. And we can build any vector from a linear combination of the standard basis, right, a finite linear combination in this case of E1, E2, and E3. Here's the definition of finite R-linear combination I mentioned in class. One thing I didn't mention in class is that we say that 0 is formed is formed by the empty sum. In other words, a linear combination of the elements in the empty set is 0, which is kind of a funny thing to say, but we say that in order that we can make a more overarching theorem later. But anyway, more about that later. Here is the proof sketch that any vector in Rn, where R is a commutative ring with identity, is a linear combination of the standard basis, right? And then we also introduced the standard basis units, the matrix Eij, right? Remember, Eij is defined to be the kth component is Kronecker delta Ik, Kronecker delta Jl. That means that this is only non-zero when both I is equal to k and when j is equal to L. This I think is worth mentioning. Here's a kind of clumsy dot style proof that any matrix in Rm by n is a linear combination of the matrix units. So the way to understand this calculation is to look at the second one and realize that if I scalar multiply this, I'd have a11 and then all zeros. This one I'd have a12 and all zeros. This one I'd have amn down here and all zeros. And if I add those together, I get that, right? So this step is legitimate. But then this is nothing more than a linear combination of E11 through EMN to build A. All right, so we can build any matrix as a linear combination of the so-called matrix units. All right, or maybe I should really say unit matrices. Well, I don't know. Anyway, let us just say the capital EIJs if we're in doubt. Now here's an alternate proof, which I was looking at earlier today, and I think it's kind of nice. If I define B to be the sum I equals 1 to m, j equals 1 to n of aij, eij for a given matrix A, then I can calculate the k-th components of B. So that would be the k-th components of this, which by definition would be the, using the definition of scalar multiplication and matrix addition, I can pull the sums out and the number aij out, and I'm just left with the k-th component of eij here, going from here to here. But by definition, that's Kronecker delta ik, Kronecker delta jl. And so what that does is it forces I to be equal to k and j to be equal to l, which basically annihilates these sums and just leaves us with akl. It just squashes the sums just down to the I equals to k and j equals to l terms. So that gives us akl. But there you go. We've shown that the k-th component of B is equal to the k-th component of A, which goes to show you that A is equal to B, which is to say that we can build any matrix as a linear combination of the matrix units. All right, well, anyway, so I keep using the term basis. We will eventually come back to what that means technically. So here was the definition that I gave for matrix multiplication, day one, in fact, at the end. And I've explained to you that this means that, there are special cases where we only have just one index here or none, right? The case of matrix column or row matrix, or what was the other one? Sometimes this can simplify down to a dot product and then there's no index. Anyway, there are kind of four special cases where either you have just one index here, or no index here, or the sum is gone. We've talked about all that in class. I'm not going to belabor it here. Dot product is a notation for taking two n-component things and combining them to get a number. If we're talking about column vectors, the dot product of v and w can be rewritten as v transpose times w. That we'll use later in the course. It's important to be aware of this. Any dot product of column vectors can be written as the transpose of the column vector times the vector again. I mentioned this, that the product of two matrices can be looked at as a bunch of dot products of rows and columns like so. All right, we've done some of those. Here's the proof of that. I think I went through that in class already. I have a slew of examples here which you should look at, right? Here I mentioned that we can define what's called the commutator for two matrices. So the commutator, this is read A bracket B or A commutator B, by definition is AB minus BA for two square matrices. So this is a kind of neat object. If it's 0, that means that the matrices commute. If it's non-zero, then the matrices don't commute. It turns out that this is fundamental to quantum mechanics. And for example, if A and B represent two physical observables, then they're only simultaneously observable if their commutator is 0. So, for example, position and momentum, typically, if you look at the operators corresponding to position and momentum, they have a non-zero commutator, which corresponds to the fact that we can't measure both position and momentum simultaneously to arbitrary precision. Anyway, as I usually say, you can learn more about that in our quantum mechanics course. All right, I shut up. Here are the properties of matrix multiplication. We proved associative in class, and these other ones can be proved similarly. All right, the key idea here is it's just like usual, except don't commute. All right. And again, to prove these, we use an index calculation. All right. Properties of transpose. I think I've I did the sock shoes. We proved sock shoes in class, which is unfortunate because that's actually a homework problem of yours. Oh man, I solved one of your homework problems. For shame, for shame. But I'll get over it. So this is another property transpose, like the transpose of the transpose is the matrix again. If we have a constant times a matrix, it's the constant times the transpose of the matrix, and also the matrix, the transpose of a sum is the sum of the transposes. So everything in here except for 2 is like really easy to prove. And like here's the proof of, I proved both. I think I'm proving both 3 and 4 simultaneously here. All right, moving along. So the next thing up, so I'm sorry to spend 10 minutes of this video just basically reviewing things. That's more or less where we got to at this point, all right? So I'll probably make an announcement. You can skip to the 11-minute mark if you want to get to the new stuff. All right, here we go. So this is an interesting calculation. If I take a 2x2 matrix, in particular 1, 2, 3, 4, one of my favorite matrices, and the vector 5, 7, I multiply them, I get 1943. If I take the same matrix A and I multiply by 6, 8, I get 2250, all right? On the other hand, if I was to multiply the 2x2 matrix 1, 2, 3, 4 with the 2x2 matrix 5, 6, 7, 8, what I get is 19, 22, 43, 50, which is exactly what we got before, except like that, right? In other words, you can think about putting these two multiplications of matrix times column, as a matrix times a matrix, all right? In other words, here's the pattern. The pattern we're seeing with these 2x2 matrices is that if we look at it, B is formed by concatenating, or if you like, gluing together the matrices the vectors V and W. See, there's V, there's W. And what we're seeing is that A times B is A times VW, but really it's AVAW. This is the so-called column by column matrix multiplication rule. All right, and that turns out to not just be true for 2x2 matrices, that is a general matrix identity. All right, so if we have two matrices which we can multiply, we can look at the matrix multiplication of A by B as a concatenation of multiplication of A by each column of B glued together. So like AB is really, of course B is written, column 1, column 2, column P, and we can rewrite this matrix multiplication as A times the first column, A times the second column, glued together with A times the pth column of B. All right. Now to prove this, you can look at the ijth component of that and the ijth component of this and show that they're equal. All right. Now once you know proposition 2 I showed you an example of why it's true in 2x2 case. Of course, that's not a proof. But one of the beautiful things about linear algebra is often whatever we see happens for the 2x2 case, it's often instructive into what generally happens. It's not always the case, but often, even at the level of 2x2 matrices, you can see the thing that separates matrices from just numbers, commutative numbers. All right, another thing, in addition to looking at matrix multiplication as this column by column rule, or the concatenation proposition as I sometimes call it, you can do the same thing for rows. All right, if I have A, B, I can look at A as a stack of its rows times B, and it turns out that this multiplication is really, the first row is like row 1 of A times B, the second row is row 2 of A times B, and so you can look at it as just multiplying each row of A by B separately and just stacking them together like that. In fact, to prove that this is true, we can use the sock shoes identity paired with the proposition that I just mentioned up here. All right, here's the proof. It's a little bit sneaky, the proof. A transpose. First of all, I'm going to let the rows of the rows of A I'm labeling R1 through Rm. All right. Then A transpose has the columns which are the transposes of the rows of A, like that. And then I can multiply B transpose A transpose using the column by column multiplication. That's B transpose R1 transpose and so forth, right? But I also know that the transpose of B transpose A transpose is by the sock shoes rule A transpose transpose B transpose transpose, also known as AB, right? So if I look at equation star, right, which has B transpose A transpose here, and I take the transpose of this star equation, then what I get is this is transpose is equal to AB, but on the other hand, if I transpose that, I just get each column here being the row of the new matrix, right? But then again, using the socks shoes identity on each row separately, I get, for example, R1 transpose transpose B transpose transpose, which of course is just R1B, and then R2B, da-da-da, RMB. All right, and so there you go. That is the row by row multiplication rule. You're like, well, this is exciting. Are there other ways of looking at matrix multiplication? Yes, there are. Here is yet another way of looking at matrix multiplication. We can look at matrix multiplication as a sum of outer products. If I have A, I have B. I can also look at AB as like column 1 of A times row 1 of B, plus column 2 of A times row 2 of B, all the way out to column n of A times row n of B. All right. And so this would be a sum of n things. And each one of these is itself a m by p matrix. See, because I gotta find a marker. Uh-oh. My kids have dried this out probably. It's probably not gonna work. What column, how big is a column vector in A? Oh man, this marker's dead. Oh well. How big is a column in A? Think about this. Column, so A is what? M by n, that means that this is a m by 1 matrix, right? How big is a row in B? Well, B is n by p, right? So that's a 1 by p. So each one of these that we're adding together, each one of these summands is m by p. We're adding a bunch of m by p things together. We get, of course, the net result of an m by p matrix, which is, well, that makes sense. Now, as with all of these rules, to prove this, you can look at the ijth component of each side and show that they're equal, which is what I do here. All right. Now, probably the most important case of that proposition I just shared with you would be this corollary. All right. If we have a matrix times a vector, then we can look at that as v1 column 1 plus v2 column 2 da-da-da plus vn column n. We'll talk a lot about this in the weeks to come. This is the looking at a matrix column multiplication as a linear combination of the columns of the matrix itself. Right? This is an important case. All right, very well. So I've introduced the next subsection here is about the matrix units and the standard basis. So there are just a couple of really important rules that we'd like to know for various calculations. One of the important things to know about is that if I take a matrix, an m by n matrix, and I multiply it by the ith standard basis factor, then what that does, all right, let's see here. There's a slight correction here. This is supposed to be like a sub k. That's a sub k. That's supposed to be a sub k. It's just I messed up the coding here. No big deal, but this AJI, what is that? Well, that is the, if you look at that, that would be column, excuse me, the ith column of A, right? And it would be the jth component of that. Just to emphasize what's going on here. So we have that the jth component of that is equal to the jth component of that, which means that AEI is equal to the ith column of A, which is what I have boxed down here. All right? And I definitely do not need these parentheses here are spurious. Brackets are not necessary here. I don't know why I have those brackets. I have them here too. I'm not sure where those come from, but we should delete those brackets. They're not necessary. I wouldn't say that makes it wrong, but it's definitely it's not right. In a sense, it's bad style. All right. Let's see here. This one. So here we're looking at the transpose of the ith standard basis, which would give us a row that has 1 in the ith position and zeros elsewhere. If we take that and multiply by A, what we get is this, which gives us Aij, which, by the way, is equal to the, let's see here, that is row I of A, the jth component of that. All right? which goes to show you that EI transpose A times EI transpose times A gives me the ith row of A, since this holds for all j. All right. So to pick off the ith column, multiply by EI on the right. To pick off the jth row, multiply A by EI transpose on the left, right? Example 20 I mentioned in class already. Remember, if we have the standard matrix and we multiply them like that, we get Kronecker delta ij. Of course, you might recognize this from the previous section. We could also write that as EI dot EJ, right? I mentioned that this actually goes to show that the standard basis is orthonormal, but that's a foreshadowing comment much later in the course, okay? I've also showed you last, I think Friday, that we can build EIJ as this product of the standard, the basis vector and its transpose, right? I think I put a bar on one of these because they're possibly different sizes. M doesn't have to be equal to n here, right? So if I was to similarly adorn them here, I guess I'd put a bar here, and a bar here, and a bar there, and a bar there, and all right, I think I got it. And a bar there. You know, but if there's no danger for confusion, you can skip the bars, right? All right. I think it's still part of Liberty Way. I think it is. Yeah. All right. Now, now, you might wonder, well, what happens if you take a matrix and multiply it by EIJ? All right. Suppose it's the right size, so it makes sense. All right. So A would have to be some like a blah by M matrix. Oh, excuse me, a blah by N matrix, and here EIJ would have to be a NN by something one. You know, without further details, it's not at all clear how big EIJ is here, okay? As long as the, let's see here. Let me shut up and go on here. So A, EIJ, KL, if we look at that, then by definition of scalar multiplication and matrix addition, it's a sum P equals 1 to N, AKP. So I'm supposing here that P is what? A is what? It's something like, well, it's got N, N columns, right? So that means that the EIJ must have N rows. But anyway, so by definition, this is Kronecker delta IP, Kronecker delta JL, and so we put I, P equals to I, right? And that leaves the Kronecker delta JL here and AKI. And so this one's actually requires a little bit of thinking, but if you think about it a bit, you can see what we're doing is we're putting the ith column of A into the jth column of EAIJ, and everything else is zeroed out. So it's kind of weird, but that's what it does. If you multiply by EIJ, you end up zeroing out everything but moving the ith column to the jth column spot. Yes, Matthew?
Can I put Derek's inside Derek's house?
Yeah, you can do that. Have fun. All right, this commercial break brought to you by Matthew. All right, where are we? Oh, so here's a specific example. I take my favorite matrix 1, 2, 3, 4. I multiply by E1, 2. See what happens? We move the first column to the second column, and everything else is zeroed out, right? And just for kicks, what happens if we multiply by E1, 2 on the left instead? Well, looks like what that does is it moves the second row to the first row and zeroes everything else out, all right? You might wonder, why are we doing this? I don't know, just for fun. No particular reason, really. The next example, on the other hand, is actually useful for many theoretical calculations. Probably some future homework of yours will be much easier if you use this. Anyway, here it is. If we do EIJ times EKL, here I and J and KL are arbitrary. Look at the MN component of that. All right, so then by definition of matrix multiplication, that would be sum over P, M and N here, which gives us this bunch of Kronecker deltas. And so that forces J to be equal to P, P to be equal to J, and P to be equal to K, right? and the Kronecker delta IM and the Kronecker delta LN, they're left over, but hey, if P is equal to K and P is equal to J, that means that J and K are both equal, so we're just left with this. All right, and so here's a specific example of it with I and I, J, K, L being 1, 2, 3, 4. All right. So if you look at it, that is what's going on here. We need well, that's going to be 0, right? So it looks like we're going to need these two numbers to match up if it's going to be non-zero, right? So anyway, in general, well, if you look at this, I mean, I don't know. I'm trying to explain this calculation, but really it just boils down to this. If we take this and that and put it together, delta IM delta ln, well, that's equal to EIL, the MN components of that by definition, right? So I'm just identifying that as the MN components of that, and then there's a Kronecker delta JK that survives. And so there you go, there's the formula. EIJ EKL is equal to Kronecker delta JK EIL. So the product of two matrix units is again a matrix unit, and it's only non-zero if this J and K happen to match up. So, all right, anyway, there it is. And then finally, a probably more important example is to combine the row and the column thing we did before. So if you think about it, what would yeah, I had to cover something. Where's my, sorry, I need a prop. Oh, this fork will have to do. There we go. So if you cover up A times EJ would be the jth column of A, right? What happens if you take the jth column of A and multiply it by EI transpose? Well, that picks off the ith row of the jth column. What is the ith row of the jth column? It's nothing more than Aij. So this shows you that we can, we can calculate the component of a matrix by sandwiching it between a standard basis transposed on the left and just a standard basis element on the right, like so. And so we can select components by doing this left-right multiplication by the standard basis. And there you have it. That's the formula that's sometimes useful. And then in the summary, we have these beautiful results, which we can refer to. So next up here, I'll stop the video and start again here in just a minute.